Okay. So good afternoon, good morning, good evening. So thank you all to join us again for another very interesting talk that we are going to have today by Dr. Yervant Zorian from Synopsys USA. But before giving the floor to him, I would like just to announce some next events. So next Wednesday, we have a very special event that we have invited Professor Michel Robert from University of Montpellier. He was the former president of the university, and he has done a book about assessment in higher education and research. So he has a large experience in about this important subject. And just after his talk, he's going to be joined by Professor Raimundo Macedo, Professor Marcelo Lubaszewski, Professor Thiago Bali, and Professor Avelino Zorzo to discuss about this important subject. So don't miss next Wednesday, 1:30 p.m. And next Friday, then the next CASS talk will be with Professor Fernando Silveira from Universidade da República Uruguay, talking about wearable medical devices, sensing and powering from a distance. Then on July 9, we have a talk by Elkin Roa, Universidade Industrial de Santander, Colombia, about hardware security instance to secure IoT sensors. And then we have each week another talk. The week in July, we still have a talk by Vladimir that from California, and many others that I don't have the flyers yet. Then, if you lost the talks that were done last year and also this year, you can address the YouTube channel of CASS Rio Grande do Sul chapter, and then you have there all the recorded versions of past talks. Normally, each Tuesday there is a new one that was recorded, and much more other events that were organized by our chapter. So it now is more than 90 talks available there. Then next end of August, as you know, you have the SBCCI conference, but the deadline has already gone. But you still can participate in the Chip in the Fields to the workshop on circuit and system design. The deadline is soon, in 4 days, June 29. And also the student forum, same deadline, June 29. So if you have not yet submitted your paper, you still have some time to do it. Then end of February, but this year is in reality beginning of March, we have LASCAS, that is the CASS flagship conference in Region 9. That means the CASS International Conference in the region. And a set of extended versions of the best papers are published in TCAS 1 and TCAS 2. The ones that will be selected for TCAS 2, they will appear in the journal in the month of the conference. So they will not appear in the proceedings, just an abstract in the proceedings. And considering also the presentations during the conference, some papers will be invited to prepare extended version to IEEE transactions on circuit and system 1, special issue. Then LASCAS 2023 will be in Ecuador, and LASCAS 2024 will be in Punta del Este, Uruguay. So another nice location. So being a member of CASS, you have a large set of opportunities to promote activities, several ones with funds that are provided by CASS Society. So there is the student design competition that you can start your team and prepare your projects to compete for the edition 2021-2022, where the finals will be in ISCAS May 2022 in Austin. Then there is the CASS outreach calls that you can submit any kind of activities, the seasonal schools, the predoctoral grants, the student chapter grants, the student travel awards. that now, as we are having mainly virtual conference, it can cover also the registration of the student, paper awards, chapter of the year awards, other society awards, and the CASS distinguished lecture program. So this is just a very short set of opportunities. So if you have an idea to do something interesting, just talk with your chapter chair or your CASS student branch and submit the proposal. So this student design competition has 3 steps. First one at chapter level, second one at the regional level, and the winners in each region are invited for the finals. And then there is some nice awards, and also the CAS supports the travel of 3 student members of each team to go to the finals, covering the travel, stay, and so on. Also, now is a nice moment if you are not yet a member of IEEE, and if you are a student or graduate student, because the student and graduate student membership have a 50% discount. I don't know for how long it will stay this promotion. They have just to put the code future50. So if you are not yet a member, please consider to join IEEE. That is the global professional network on our field. So today we are here to attend a very interesting talk by Dr. Yervant Zorian. So who knows him knows that all his talks are always very interesting ones. So today is about the safety and reliability challenge in today autonomous vehicles. So Dr. Yervant Zorian is a chief technologist and fellow at Synopsys. Formerly, he was a vice president and chief scientist of Virage Logic, chief technologist at Logic Vision, and a distinguished mentor of technical staff at AT&T Bell Labs. He is currently the president of IEEE Test Technical Council, that also promotes here in Latin America the Latin American Test Symposium. And he's the founding chair of the IEEE 1500 Standardization Working Group and an adjunct professor at the University of British Columbia, Canada. He served as the general chair of the 50th Design Automation Conference, the 5th International Test Conference, and several other symposia and workshops. Dr. Zorian holds 44 US patents, has authored 5 books, published over 350 refereed papers, and received numerous Best Paper Awards. He's a fellow of IEEE since 1999. Dr. Zorian was the 2005 recipient of the prestigious Industrial Pioneer Award for his contribution to BEAST, and the 2006 recipient of the IEEE Hans Carlson Award for Diplomacy. He received a master's degree in computer engineering from the University of Southern California, a PhD in electrical engineering from McGill University, and an MBA from Wharton School of Business, University of Pennsylvania. So this is just a very short resume of the large set of achievements that Dr. Zorian got till now. So it's a pleasure to have you here today, and thank you very much again to accept our invitation. So I can give now the floor to you to start your talk. So
thank you. Thanks a lot, Ricardo. Thanks a lot for inviting me, and particularly thanks for creating this series of talks. I visited the YouTube site. They're exciting. They're quite wide range and very prominent presenters and topics. So I'm pleased to bring my contribution to your series as well. And in this case, this particular presentation will be related to autonomous vehicles, to the safety, reliability aspects of them. As you know, we are surrounded by change all the time. The only constant thing that we have is change. Particularly during the past 1 year, we have seen so much change. And in everything we touch, in every equipment we touch in our life, we see change, smartness, and increased smartness as you move forward. And that smartness is in small and large elements of our life. And by doing that, we see that change is not new. We have seen it through the past 4 decades. Uh, First, we saw it in the compute world by introducing personal computers after having large computers for a long time. Then the change came to the communication space, networking with the internet revolution, and so on. And then we saw the change coming through the smartphones, tablets, and so on, which is the mobility. All the mobile devices that we play with constantly. And then this last decade, our change is more in the AI domain, a 5G in the communication, which is enabling lots of smart equipments to be intelligent, mobile, communicative, and being able to help us in our natural life. That's where autonomous vehicles come to picture, and they can play a big role. And they're the most critical one that we all use are the cars, perhaps. All the autonomy that the car is taking over from the driver, which is great because it's using what the driver would have done in most of the time. So a large percentage of what the driver would have done has already moved to the autonomous system in the car. But we also see increase in robots for our personal lives, for our industrial lives, in the factories. We see it in the space, the three-dimensional. So not only the cars, which are two-dimensional movements, but three-dimensional movements such as the drones and so on. Now, what is common among those? What's common is the fact that they are fully electrical these days, most of them. They are also autonomous, and they're changing intelligent, that is, and they're changing the style of our life. If I take our cars for an example, the cars have moved from being propulsion based to being electrical based. We have seen the intelligence of the driver in terms of being autonomous, moving to the car. And also we saw that an impact is already happening on the economy, because by having autonomous cars, you can do more sharing of cars and so on, and thus over the long run impacting the traffic, having lesser traffic, having lesser need to parkings, having less congestion in the center of the cities. So all of that is happening because of the technology that's coming in. And today we'll talk about the technology mostly, not the economic impact or the implications about it. And what kind of technology is helping us do that? It is the software and the hardware in these autonomous engines. For a car now, today's cars would have a very complex piece of software. We'll have about 100 million lines of code in my car today, which communicates 4 terabytes of data per day. Even if when you're not driving during this COVID period, the car is consuming lots of energy. I spend about 4 miles a day without moving the car. It's because of the multi-terabyte communication that's happening between the car and the cloud. So all of these are happening because we have supplied our cars with various electronic systems, from the powertrain to the safety mechanisms, to the self-driving intelligence, to the infotainment. All of those are different elements that are coming in. And we're seeing the increase in the complexity of the cars from electronics point of view to go up. But from the mechanical point of view, it's being simplified. The new cars are much more simple mechanically. That's why we see new car companies coming up, such as Tesla, for several years now, which is a light car company, because if you open the car, there's much less complexity in the mechanics of the car in there. Instead, there's a network of chips, and there's a constant amount of software which gets upgraded on a regular basis. Similarly, we're seeing many electrical car companies around the world that are popping up. We see, for instance, the amount of electronics in the cars here, how it has increased from the 50s, where about 1% of the car cost was the electronics, to at the end of this decade, we'll have about 50% of the cost of the car in its electronics. Today, because of the electronics market limitations, we're seeing a backlog of cars, so we're seeing lots of problems because of the supply of the chips to the cars are not sufficient. Therefore, we don't have sufficient amount of new cars these days around us. On the software side, we also see a constant increase in the software, and that will go up as well. So both the hardware and the software are dominating the cost of the car. And why is that happening? That's happening because you have intelligence in the car that is needed in every sense, in every system inside the car. And it is getting centralized more and more. In the past, we used to have hundreds of ECUs, controller chips, that were sitting in different corners of the car itself, of the system. Today, we have much less ECUs. We are collecting them and centralizing them. So you have a more intelligent engine, centralized, dealing with lots of points around the car to actuate, to control, and to provide the mechanisms for them. Also, we're seeing complex chips for driver assistance, for because of the vehicle-to-vehicle communication. One of the newer things, as you know, is the two vehicles talking to each other. Another reason for the complexity is the fact that we're seeing new types of sensors, imaging ones, LiDAR ones, radar ones, and so on, and their numbers. Okay, so as a result, we also need to have, of course, safety. We also need to have intelligence in security, and we'll come to those shortly. One very important component in all of this is the AI aspect. Is the AI algorithm being used in various domains of the car. So various chips or various subsystems in the car are using AI as well, and we'll come back to this too a bit later, especially in the ADAS chips and the infotainment chips of the car, bringing in lots of information from the sensors, but pre-processing them in the car and then sending them to the cloud, and we'll see what happens later. Now, all of this is happening because we have the car requirements coming from the OEMs. The OEMs are the car manufacturers. The tier ones are the subsystem suppliers, and then the component suppliers are the ones who provide the chips for the cars. Even though this traditional three slice structure of this industry is changing also now. Now we're seeing the tier ones, the OEMs doing tier one's job, the tier ones are doing their own chips. So because of the changes, the recent changes in the car electronics industry, even the major players are changing their roles over time. Typically, you would have received the requirements from the OEM to the tier ones, and then the chip suppliers will create the chips. Of course, the chip suppliers will work with the rest of the industry to get the necessary chip design tools, chip designers, chip manufacturing companies, IP companies, and so on to create the necessary chips for the cars. And we'll concentrate most of the talk today about the chips. But one more thing to remember prior to that is that all these systems that we're talking about are not isolated systems. They are all connected with each other. So the connectedness is also part of this issue inside the car. More importantly, outside the car. The car is connected to the cloud, and we will see that the useful part of that is getting AI information from the cloud, but also the dangerous part of that is getting security issues, again, due to its connection to the outside world. As a result of that, we see safety, security, and reliability being very important elements in our cars, in all these autonomous vehicles, in fact, where you see that the infotainment is important, the gateway is important, but each one of them has the issue of ensuring safety, security, reliability. Reliability is over time aspects of it. Of course, there are more elements that we care about. They are not our topic of interest for today. That is the software, the machine learning, the power aspect of them, and so on. And we see that other products besides the cars do also care about the same things. In avionics, which are also autonomous vehicles, industrial, which are also robots in industry, for instance, or IoTs, small drones for your cameras and so on, they all have similar kind of missions. They are mission critical ones because they can create dangers for life. Therefore, we need to take care of them clearly. Now, if I look at the autonomous vehicles, especially on the automotive aspect of it, I see that the chips in the car, for instance, are not all the same. There are different categories of them. There are categories, if I go from the right-hand side, there is um, the basic controllers, if you want, that are sitting there. Then in the middle, I see infotainment and car-to-car communication. And then I have the driver assistance systems, ADAS, which is more the intelligence of the driver put into chips. But if I look inside the chip, coming from the IP industry, I like to look inside it and see what kind of boxes are needed. I would notice that some of the boxes are similar, some of the boxes are different. As we move forward, we see the complexity of those chips changing. The most complex of those are the ADAS chips. And ADAS chips need to have in them high-end processing power. They need to have artificial intelligence accelerator. They need to clearly have security and safety. We'll talk about that a little bit more. Lots of communication protocols talking to the outside world, outside the chip, I would say, whether it's MIPI for videos, HDMI, PCIe, so lots of high-speed PHY communication. And the technology that is supplying all of this is changing quite fast, changing in the sense that the newer ADAS chips were just a couple of years ago, 16 nanometer technology was good enough in terms of speed, area, power. Today is not. Today we are already in the 5 nanometer, which will be an issue. We'll talk about it in a bit, because before the technology gets matured, we are already starting to use it in mission critical applications such as self-driving of cars. Okay. The others, infotainment does not need that far. So today the infotainment chips can be at 16 or 14 nanometer. Again, the gateway chips, they can be also at 16, 14 nanometer. The most critical ones are the ADAS, as I said, because of the AI aspect of it, the speed that is necessary for it, we are forced to go to smaller and smaller technologies. So today, if I look at the ADAS chips, I already see that about more than 20% of the chips today are already in 5 nanometer. Somehow behind, of course, they're coming. But the infotainment and the powertrain chassis sensors are still at earlier stage technology, meaning older technologies. Now, what is the difference between this if we compare it to another application? With the autonomous vehicles, the cars, the drones, and so on, we have a range of technologies. If I compare it to mobile equipment, the range is smaller. We see that the design size is slightly different, but most importantly for me, it is the conditions under which this is running. For instance, the temperature. If you are talking about your cars or drones, the range of temperature is much wider than your mobile phone, which is in your pocket or in your room and so on. So you're dealing with wider range from -40 to +155. Therefore, the preparation of that chip, its tolerance, its quality, its reliability should meet that. Also, the life cycle. The lifetime for mobile phones is much shorter than the lifetime for cars. Therefore, the lifetime reliability, the aging aspects, and so on are far more important in this second case. Okay. Therefore, the failure target, we look at DPPMs that are 0, and we'll talk about that in a short while. So this is just to give you a feel about the two aspects. The most intelligent ones, as we said, are the ADAS chips, and the ADAS stands for Advanced Driver Assistance Systems. Okay. Now, with those chips, what happens is that the information is collected from the different sensors around the car, from the cameras to radars and so on, from the GPS, and that information is being collected, pre-processed initially, and then sent out during the day or overnight to the cloud. That's why we had this 4 terabyte of communication. But why did we do that? We did because in the cloud, we need to continue doing machine learning on it. So what we collect as information and pre-process it in the car and ship it then in the cloud, there's a compute center where it gets interpreted and then sent back to the car to optimize the AI engine in the car. Okay, so the cars that have the companies that have more cars in the streets, they collect more information. Therefore, they have much bigger data. Therefore, the interpretation is much more meaningful. Therefore, the self-driving could be much more optimized, specifically for that area where there are many cars that are using the same ML. So being part of ML, being part of artificial intelligence, the car engines are also now, the ADAS chips, that is, are part of the overall system for artificial intelligence, which is quite large, which is growing very fast, as we know, around the world, because all the systems that we are using are becoming more and more intelligent, and they are using more and more AI-oriented approaches for that. I will not concentrate on this too much. We can talk about AI some other time. AI is something that is being used in everything, in every company. In my company, where we do EDA tools, we use AI for multiple tools that we have. Instead of doing them only algorithmically, today we can use all the past data to optimize the next data, right? So we use all the learning from previous data in order to shape the future and move on with different types of tools. Also, in the IP side of what we do, as we're building chips in the car, the IPs also need to be intelligent, and therefore the chips in the car do contain their AI corner. So it's not a single AI accelerator that is used today in the cars, but rather, for instance, the ADAS chip will have a corner of it doing machine learning. The neural network computation that's going on will be in a part of the car, and the rest will be processing it and taking advantage of it. So the basic processing will happen, differentiating between different types of objects, and accordingly taking decisions, whether it's a person or a car or an animal, or understanding the signs around you, and the different aspects around the car, is done by image processing, by understanding them and using the neural networks inside the chip. Where does this put us? This puts us in a situation where we're using advanced technologies for the car, new nodes, say 5 nanometer, and then the challenges of doing a chip in that domain is all the FinFET challenges that we have today. They are similar to everybody else. So we have all the power, performance, area, yield challenges. But not only that, because of these autonomous vehicles, also we have safety as a challenge. We need to make sure we're at the right safety level, right reliability level, right quality level as we produce the chips, okay? But also the right security level, because security, safety, reliability, and quality any one of them can be at risk if we're talking about these mission critical systems. So concentrating on those, we need to abide by measures, we need to abide by standards, make sure that the quality is fine, so that the silicon life cycle, the chip throughout the life, is done properly. And as we know, the silicon, to maintain the life, we just don't produce it in volume. Of course, we do the chip in volume, we produce it, we have to make sure that it's at the right quality level and so on. But we need to invest in that chip design early on to characterize it, to debug it. So we need to design the chip for characterization and debug. And later on, we need to build into our design capabilities to ensure power on self-test, to ensure periodic checking, to ensure real-time monitoring. All of these things could happen if during the design stage we invest in the cars. So it's a silicon that goes in the car, it has a life cycle, but to manage that life cycle, we need to be able to invest. We call this, long time ago, infrastructure IP, that is intelligent IP for DFX purposes. And the purpose of that infrastructure IP is maintaining the health of that silicon during the life cycle. So let's talk a little bit about safety, reliability, and quality, concentrate a little bit on each, and then we will see that these are all needed for the field eventually, but they are all incorporated in the design stage, and then utilized later on to take advantage of them. Particularly for these automotive designs or automotive equipment, what we need to do, we need to ensure very, very high quality production test, Okay, we'll talk about that. To have 0 DPPMs, we need to ensure that every time I power on my car, there is a power on self-test going on, to ensure that nothing happened during the life cycle, and that's a reliability issue. No aging factors, or at least we can clean them as they come in. And then in the field, safety, security measures, and so on for anything that could happen during mission mode. We need to contain them. We need to have tolerance for them, and so on. Okay. As we are moving through the technology nodes, we see that those approaches are changing as well, and the stringency of those approaches. And we monitor. At Synopsys, we look at how long each node will take, and how the first 500 designs, how did we ramp up, how fast did we ramp up. Some nodes are ramped faster, others not. Today, we are already in the 3 nanometer domain. Okay. And to do that, we need to have solutions that match these. That match the exact nodes, and to make sure that they reach the right DPPM level. And DPPM, by the way, means defective parts per million. Okay, and that is 1 part per million can be escaped if DPPM is 1. But given the automotive situation today, all the decision making that we are converting, we are transporting from human to machine, we need to have much better than 1 DPPM. We need to have 0 point something. So we are looking at measuring it by DPPB, that is defective parts per billion instead. Okay. To do that, of course, we have to go to every chip. To do that, we have to go inside the chip to make every block intelligent enough to have the different safety, security, quality measures in them. And the chip is rich with many types of blocks these days. And this is one sample set, as we have seen earlier, also from different types. So what do we need to do? We need to think of an IP at a time. And as we are preparing that IP, build in the quality, all the self-testing, self-diagnosis, and so on in advance in that. Make sure they are accessible via different systems. So it's not only isolated with its patterns, but the accessibility is there at the subsystem level, and also the accessibility is there at the SoC level. So accessibility is a key element. Now, depending on the box, we do different things. If I have a mixed signal IP, I need to have that mixed signal IP have all its self-test capabilities built in order for it to be self-tested, not upon manufacturing only, but also in the field later on. Okay, so all kinds of interface IPs that we do at very high speed, PHYs that we produce, we make them each self-testable. We make them each ready for diagnosis, for loopback modes, for characterization modes, and so on. And for that, we see that complexity is going up constantly. We see that the high speed and the more complex PHYs, for instance, DDRs, USBs, and so on, have many pattern sets, whereas the small ones, the sensors, the monitors, will be simpler. The medium ones will be ADCs, DACs. So the complexity of that additional effort, additional intelligence put into those IPs will be a little bit less. Memories are the most complex, as you know, because they are very dense, and the number of memories is large in a given chip, and also the total bit count is quite high. Therefore, the yield as well as the reliability can get impacted with the memories. So that's why having a memory test and repair system intelligently incorporated would be important. To deal with every memory, we need to wrap those memories. We need to process their test and repair algorithms, have access to do diagnostics with them, and have capabilities outside to diagnose them. The problem is that those chips are shrinking, and memories, before everything else, are changing in their behaviors because different defects are acting in different ways. As we moved from planar technology to FinFET technology, we saw that lots of new defects started to come in. We saw that there are certain defects, stock-ons to appear in the fins. We see fin opens, fin shorts. One transistor is made of 3 fins typically. How these 3 fins are working with each other, all the shorts between them as well. And this is changing. It's changing in the fact that as the fins are moving from one node to the next, they're becoming taller and weaker. Okay, taller and weaker in a sense that we need to take care of them early on before they create problems. Where the fin height keeps increasing, they're taller, but the fin width keeps shrinking, they're becoming narrower. And that's why with every technology node, today we are at 3 nanometer, we need to understand their defectivity. We follow a certain advanced inductive fault analysis method to inject defects and understand their behaviors to control that quality. And we see that the same defect, for instance, this particular defect, which is a resistive fin open defect, will act differently, will behave differently if I am in 7 nanometer or 4 nanometer. If I'm in 7 nanometer, detecting the same defect will take a particular sequence of operations in that memory. If I am in 4 nanometer and 5 as well, I will need another set, which is different. Therefore, from node to node, things are changing. Therefore, that's why in our case, what we do is we analyze every node. We started with 28 planar technology to the first FinFET in 16. We moved to 7, we moved to 5, and now 3. And in each case, we create different test algorithms accordingly based on the injected defects and seeing their behaviors. And those algorithms, therefore, will go in and sit in an engine that will provide the solution for you. So these are all intelligent efforts that have to be done all in advance. And as we're moving to newer technologies, moving from 2-dimensional planar to FinFET, which was 3-dimensional, and now to gate-all-around, the GAA technology with nanowire, nanosheet will again bring us new types of defectivity. We have to understand them. And the memories themselves also are going to 3-dimensional. That also is a challenge that we need to look at. Now, all of these are added by repair aspects. We need to ensure that yield is good, and therefore repair is there in multiple ways. Particularly in automotive, the repair has to be very fast. We have to accelerate the repair because when you power your car, you don't have time to wait in order to fix the yield aspect that is pre-programmed in your fuse box inside the chip. Of course, understanding defectivity is important as well when you're dealing with new nodes. Again, for the automotive quality, we need to have all the diagnostic capabilities built in, from understanding which memory is failing to understanding which exact location of defect is there. And this will allow us to see where are the defects and deal with them accordingly. And then analyze them, do visualization, do correlation, do statistics, and so on from there on. Now, let's not forget that we shouldn't only look inside the chip, but also there are memories outside the chip, outside the SoC, outside the ADAS chip, which are DRAMs. To do that, we also need to interact, to sit inside the logic die and do external memory testing. Okay, so something we learned over time as well. If you have DDRs, if you have HBMs sitting outside, we need to put the engine in the SoC and test the memories externally. Again, to ensure that they are healthy, not only upon manufacturing, but also during the life cycle. Upon power up, every time I power up my system, my SoC will run the test and repair and test and repair all the memories, DRAMs connected to it as well. And then this entirety will do the job. So that we call it periodic testing from time to time. Okay. On the logic side, we also need to ensure the quality of the logic. Particularly in automotive, we need logic BIST because it's not only the manufacturing, but also in the field, you need to test that logic. And to increase the coverage of logic BIST, we all know that we use test points. And those test points are based on analysis of my logic blocks, either placement based or timing based. And I insert the test points and get very good coverage. So logic BIST at large has a couple of issues to be looked at. One issue is the X tolerance aspect. We need to have good X tolerance. Second is the coverage aspect. We need to have test points to get high coverage. And the third is having multiple seeds. A single seed may not give us enough coverage. If I run multiple seeds, then I get much better coverage. See, this is with 1 seed, with 5 seeds, with 10 seeds. So therefore, we need to have an X-tolerant logic-based solution, as we call it XL-based, and insert the test point in it in advance, and then have multiple seeds managed to get the highest coverage possible for in-system testing. As we'll see later, in-system testing will have certain requirements. Each time you do your power on self-test, you need to have a certain level of coverage to reach 99% if you're shooting for ACD. That's why when we put everything together, whether they are the memories or the high-speed analogish blocks or the logic blocks, we need to have all the engines prepared and managed via the hierarchy. And coming in manufacturing from the tab, the JTAG tab, exercise it and have the entirety work together. So this is all allowing me to do quality. Next is reliability. For reliability, what we have is we have a couple of issues. One is aging. So transistor aging is important. Therefore, aging monitors are needed for these systems that have long life, cars, 15 years or so. Also, reliability against soft errors is very important. And as we know, as we are shrinking the dimensions, the memory bits are becoming much closer to each other. Therefore, multi-bit or errors are happening much more. For multi-bit errors to be detected, we need to have and corrected, we need to have intelligent ECC systems that don't look at one error at a time, but rather can look at multiple errors that would have happened because one hit is causing multi-error situations. So to do that, of course, we need to have different codes that can do multi-bit correction. And then you have an ECC that is intelligent enough to handle multi-bit error correction. Also, the new standards are requiring more, where typically the error correction is at the data level. Now we need address-wide also correction. We need also error injection capabilities to be added to our systems. So this is adding to the solution, to the space of the solution much nicely. So ECCs for reliability are very good. Having fit rate planning is important as well to get the right amount of ECC. You don't need to put ECC in all the memories at the same time and none of the memories as well. You can have a subset. For that subset, you need to do a proper planning to see which memory needs how much amount of ECC, no ECC at all, or detection only, or correction as well. So this gives you a view about the reliability as well. Finally, the third component is safety. Safety, as we know, is not something new. In the industry, we had safety for a long time, for mission critical, for medical, for machinery, for airplanes, and so on. And there were many standards. But recently, for moving vehicles, we created this new standard called 26262. It's an ISO standard. It's an ISO standard that has multiple levels, depending on the risk potential. It can be A level, B level, C, or D. The ADAS chips, the driver assistant chips, will be at the D level, for instance, okay, because they are critical systems for us. So self-driving would require ACD, which is more stringent. If you're doing not self-driving, but driver assistance only, then B level or C level would be sufficient, depending if it's a radar or a camera and so on. So those levels are incorporated into the design. So when I'm doing typically my design from top down and then my verification from bottom up, now I need to do more. I need to also have safety incorporated. So this ISO 26262 will require that I go through all these steps, okay, to incorporate the safety mechanisms, the safety features, and then have the safety manuals, the safety reports come out of it. And this is at every level, from IP level to chip level and later. So to do that, I need to put certain mechanisms for safety. And we know these things. We know parity, we need protection, we need triplication, duplication. There is a menu of different possibilities of functional safety mechanisms. But I have to choose them. To choose them depending on what is more important for me. For instance, if I look at replication, doubling, tripling, triple modular redundancy is expensive, but it gives you much better tolerance, much better safety. Whereas if you do basic detection or parity, it will give you less effectiveness. But depending on the situation, you need to decide in each one of your IPs how much of that to put and how much complexity to add to the IP in order to make it safe. As a result, I would see that my IPs will have certain protection mechanisms, such as detection and so on, redundancies, such as duplication, triplication, and many other ways of protecting them. So that's a science by itself, the safety mechanisms and how you fit them, for which we do have analysis tools and so on to make sure that they are well analyzed. And as a result, you get to the level necessary. Once you put all that, for each IP, you need to certify it officially by third-party certification, and you need to have either ASIL A, B, C, or D level. This happens to be an ASIL D oriented evaluation where it satisfies. Therefore, the user can take it and incorporate that IP inside the chip. Okay. So for every IP, when you build it up, it will give you necessary to go to the field. And now we have to use it in system and in mission mode. So in system, what do we do first? We do the power on. Every time I power on my chip, I have to run all the self-test mechanisms that are there. The logic-based, the memory-based, the interface IP-based, the analog-based. And it will need to be run one time with very high fault coverage. This is upon power up. But I will see that I need to do more than that as well. To do this, I need infrastructure. I need to have my different engines, the logic-based, the memory-based, and so on. But I need to have a scheduling manager such that I click it and everything runs smoothly, nicely with each other. Now, to do that, of course, I have to run different complexity algorithms. The complexity of the DPPM algorithm that I run in manufacturing for FinFETs is not the same that what I will run during power on. It's much less, okay? So the selection algorithm that we do is lesser complexity. And later, when we will see periodic testing, even there it is simpler or less complex because what you're checking periodically is not the aging faults or it's not the manufacturing faults, okay? So therefore, your memory-based engine need to have multiple algorithms built in. In the field, when I'm in mission mode, I have two types of things. I have ECC, the error correction that we saw a little bit earlier. It is very important to have it fully done, but also transparent-based, which is periodic. That is running every so often. The 26262 standard requires that we do it every 100 milliseconds with 99% coverage. So all the blocks that have their bits to run in a periodic way need to do that job on a constant basis when you are in the field, when you are driving your car. We have done some joint publications. This is one with Intel about that specific aspect, about the periodic testing and how it works. So at periodic testing, we'd run one slice of the chip, then the next slice, then the next slice, and then manage it all from the engine that sits there. We call it the safety manager. Safety manager, as you will see, it's a microprocessor needed for safety purposes, without which you cannot manage. I mean, you can have all of these engines sitting in there, but without managing them by a dedicated safety processor, that will not be done properly. So this is running the first slice, the second slice, the third slice, depending on their mission mode. We have done some work and we published it with Bosch around those. So it shows how a central entity, a safety controller or a safety processor can come and handle each one of those blocks. Those safety processes are special. They have to be also lockstep based. Okay, so they are dual core with lockstep. They check against each other. This is one of the safety processes that we have in our family of ARC processors that do that checking, that have ECC in them, that have various capabilities, and they are dedicated to manage the safety aspects upon power on, as well as periodically. Therefore, to look at it from next level up, we see that safety manager, or some people call it safety island, need to come in and through the APB port, talk to my total infrastructure, run my logic base, run my memory base, run my analog base, based on a given schedule for the entirety. So all of these are very nice. However, I still have one more challenge, and that one more challenge is security. To ensure security, especially that we are connected to the outside world, and the car, through its infotainment system, for instance, can receive hacking, and which may replace its embedded software, which may impact my actuators. So I need to close the doors or secure the doors, right? And secure the doors at different times. During the running operation, during the mission mode, I have to continuously check for threats, continuously check for communications. During the power on and power off modes, again, I need to make sure that during the power up, nothing is being interfering. We validate the software, everything is correct. And also power off, nothing is being stolen from my car when I am in power off mode. To do that, I need a trusted environment. So my final point is that the trusted environment needs another processor, which is for security purposes. We call it the root of trust processor. So a processor that sits inside the chip, separate from the safety processor, that allows us to secure the chip. That allows us to look at the different runtime protection aspects, secure the storage, check the keys, do the recovery, ensure the storage elements are properly controlled. So it's one corner of your SoC sitting on the bus, but controlling all the other traffic, and especially the interfacing ports with the outside, okay? Well, all the high-speed interfaces or low-speed interfaces that we are open to, we have to make sure that the T-root does that job. Now, T-root also needs to look after the DFT or DFX infrastructure, because that DFX infrastructure can also be a place for intrusion. Therefore, we have to lock it. We have to lock at this level, at that level, at that level, to allow only authorized entities to come in and access the chip when it's in the car, okay? So all these mechanisms need to be built in the car, and accordingly, we need to control it. So finally, what do we need to do? We need to build inside our IPs all the necessary functions. We need to build the hierarchy to manage it, but we also need to have two on-chip processors in small intelligent capabilities, a safety island to ensure the safety, and then a root of trust to ensure the security. With that, I think we can cover the important aspects of our chips. As we're putting them into a very critical mode, we can control the safety, the quality, and the security of them. And not only in the cars, but also in all the equipments that will be around us that are critical. So that have autonomy, that are moving around and giving us the necessary confidence. With that, I would like to ensure that we have the basic concepts of safety, security, quality, and reliability. And I would like to thank you for your attention. Thanks a lot.
So thank you very much, Yervant, for this excellent talk.
Thank you.
So the ones that have questions, please do it as soon as possible using the chat channel. But to start, I have one.
Yes, please.
So nowadays, the amount of the number of chips in a car is very large, no? And then there is a lot of cables connecting them.
Yes.
And cables is also a source of problems of reliability, no? So how you see the possibility to reduce the amount of chips in a car to have only few ones? How you see these possibilities, no? To
Yes.
reduce all this amount of cables and so on.
There are two aspects, and the trend shows that we're moving in both directions positively. One is reducing the number of chips from instead of having many distributed controllers next to each system and so on, getting from those controllers to a centralized place. So to have less chips, to have them in centralized places, to do all the judgments and compare the results to each other. So instead of having local decisions, have global decisions at the car level. However, that brings us to the main issue that you mentioned, the cabling. If these are all connected via cables, that will increase the amount of cable inside the car, which is not only a reliability issue, it's also a complexity issue, it's also weight in the car and so on. So for that, we're starting to see cable-less, wireless communication being adopted. I know of several companies that are even looking at using 5G inside the car, using different communication protocols inside the car to be able to communicate in a different wireless protocols to ensure that communication does not require as much wires.
Okay, thank you. So we have a question by Professor Altamiro Suzin from UFRGS here in Porto Alegre. Thanks for presenting these hot topics. Many questions arise. For example, will it be feasible to route 4 terabytes for each vehicle, or this is the maximum when possible, dropping out if not connected?
It is. I mean, these days, communicating 4 terabytes is not a major issue. It is doable. It may not be needed constantly, though. The 4 terabyte that I mentioned is a daily basis to send your experience to the cloud and receive back information from the cloud to optimize your weights on your network, on your neural network. So this 4 terabytes of information does not need to be done constantly. It can be done if certain periods you're not connected, it can be done later on. But there is a connectedness aspect of it also for infotainment, for directions and so on. Being connected is important. That connection to the cloud is one aspect. The second aspect is the connection between the cars. For control, for safety, car-to-car communication is also important, which is also a certain amount of data, but that's not a huge data between car to car.
Thank you. So another question also by Professor Altamiro Suzin. I feel that the main concern in the talk was defects and faults. What means hardware security? How can we face validation at algorithm level in such complex application like autonomous machines?
Yes, we definitely need to have it not only at the hardware level, but also at the software. Today, my concentration were on the chips and the health of the chips during that life cycle. But we are not limited to that. At every layer, we need to ensure that, particularly security and safety, the risk can be at every level. Okay, so software security, software safety are very well studied fields. They are very critical, and therefore we need to pay full attention to them as well.
Thank you. So now I talk by Eric Tokuda from University of São Paulo. How do you guys in Synopsys plan to handle this plateauing of the Moore's law? How do you plan to keep increasing processing power in small well
yeah, small scale, I guess. Or yes, Moore's law, we know that Moore's law, as it was defined, it stopped some time ago. Even the FinFET nodes were not the pure CMOS nodes. They have special steps, they have special capabilities. As we move to GAA, will be even more. But I think one way of addressing the Moore's law need is not through shrinking the semiconductor technology, but also using new ways of packaging technology. That is, putting different types of functions in different pieces of silicon and packaging them together, whether in 2.5 or 3D manner. The chiplets today are becoming needed these days. So you don't put your entirety in one chip. There are two different aspects of this packaging. Either one very complex chip, you take it, you disaggregate it to multiple chips, and you put them next to each other or above each other, and you create a function. Instead of trying to squeeze everything in a single SoC, you put four of them together to do that function. That's it. Another way of doing it is mixing technologies. That is, you can make the processing engine with 3 nanometer, whereas you put other functions, the analogish functions and so on, in other technologies, but still multiple dies together. So in my mind, addressing Moore's law is not only by shrinking to go to the next node, but also utilizing the multi-die packaging aspects of 2.5 and 3D.
Thank you. So now a question by Amir Khan from University of Seville in Spain. So latency issues will be severe for such scenarios. How to tackle then when there is so much amount of data transfer and to identify the type, event, or information? It is emergency or normal come?
It depends on the both. So there is the normal communication is part of it with the regular information flow, data flow that is going on, that's being collected. But also there is the emergency. There are the warnings and the interrupts and so on. So you have to see that if a certain safety risk or security risks happens, then there are higher priority communications. Besides that, there is the normal flow of data as well. So it's a mix of the two. But the system that you're building has to be intelligent enough to handle multiple communications.
Thank you. Now a question by Professor Tiago Balen, the head of the graduate program Microelectronics at UFRGS. Can you comment a little on electromagnetic interference in autonomous vehicles and what is done to mitigate besides shielding?
Yes. Electromagnetic and many other factors that impact the health of the chip need to be taken care of. Now, if you do it particularly to one or the other, such as shielding, you have to be very direct to address different aspects. One other way of looking at it is to go to the next level. For instance, when we talked about error correction, when we talked about fault tolerance, when we talked about periodic testing and acting accordingly. All of these things are things that could happen during the mission mode. And if you see any kinds of interference, whether by natural reasons, such as these, or by bad intentions, such as the security ones, we need to be protected for them. Okay.
Thank you. So another question by Altamiro Suzin. For IP interoperability, it would be some standards in order the designer could verify.
I'm not sure that the question is very clear to me, but the IP interoperability or talking to the different IPs, yes, we need standards. Of course, the IPs themselves often are based on standards, because they're using, let's say, USB communication. That's a standard, or the DDR, it's a standard, or they're using MIPI, which is standard. So either they are using a standard to communicate for functional purposes, that's one. For the health of that IP, if I am communicating about its testability, its reliability, its other methods, so there are also standards to carry that information and to make the IPs interoperable. You know, in the testability world, we have multiple standards. IEEE 1500, IEEE 1687 are standard to access IPs and to communicate with them. And we utilize those for that purpose. So there are standards for functionality purposes, and standards for DFX purposes.
Yeah, as you can see, Suzin changed a little bit the question, talking also about the integration in the verification chain. No?
Yes, there also you need to have integration. You need to everything that I mentioned need to come through the verification chain as well. In fact, anything you are adding has to be verified properly, because you are adding to the complexity of the design. Gladly, we have nice ways of verifying the IP functions. Gladly, we have nice ways to verify the safety that we added, or to evaluate the security that we added, or to measure the quality, the testability, the coverage that we added. So all of that has its have their own verification mechanisms.
Okay, thank you. So I'm not seeing any more questions here in the chat. So if you have still have a question, please do it now. But I have one.
Yes.
So one point, as you already told in the cars, is the reliability, and some cars to increase the reliability, they use in some chips not the most new technology, but some older ones that are more reliable. No, so how you see this the use of older and newer technology in the cars? So maybe for some chips, new ones, but for a lot of chips, it's preferable to use older technologies that are more reliable, considering mainly in radiation effects, for example.
Yes.
So
yes, that was the trend actually, Ricardo. For a long time, the chips in the cars were not the most recent technology. The chips in the cars were always 2-3 generations behind, right? Because of exactly what you mentioned, the maturity. They were mature enough, therefore we were able to use them. Still, there are certain types of chips, let's say the microcontrollers in the cars, do not need to be 5 nanometer. They can nicely be 28 nanometer. Okay, so that is continuing. However, because of the intelligence that we added to the cars, all this self-driving needed, the AI for that needed, and so on, that requires much faster speed. And because you need faster speed, we're forced to go to those newer technologies. So going to new technologies is not just for fun. They would have stayed in the older technologies typically. But those functionalities require much faster communication, much faster computation, much more memories. That's putting them into the newer nodes. And the problem there is that because these nodes are not mature enough, we had to do several other things, as I mentioned in my talk today. They were mostly due to the fact that we have to use the new technologies, but we have to add new mechanisms to protect the chips, to maintain the health of the chip, right? Otherwise, if it was mature enough as before, many of the things that I mentioned today may not have been necessary, because they are using mature technology, stable technology, and so on, well protected.
okay, thank you very much, Yervant, for this very nice talk. I'm seeing no more questions here in the channel. So thank you very much. But before saying goodbye to you, I'd like to remember of the next events that are being organized here next week. So next week we have two. The first one is the special webinar and panel dedicated to the meaning of assessment in higher education and research, started by a talk of Professor Michel Robert, former president of the University of Montpellier II in France. So he has done a book about this subject, and also we are going to have a panel with the participation of Professor Raimundo Macedo, the president of the Brazilian Computer Society, Professor Marcelo Lubaszewski, that is the vice president of the Brazilian Microelectronics Society, Professor Thiago Balin, the head of the graduate program Microelectronics, that is a interdisciplinary program, and Avelino Zorzo, that is representing the Computer Science Committee at CAPES that is the responsible for the assessment of graduate programs in computing in Brazil. So I hope that you all will be able to join next Wednesday, also 1:30 p.m. Brasilia time, that means GMT -3. And on next Friday, we have Professor Fernando Silveira from Universidade da República, Uruguay, talking about wearable medical devices, sensing and powering from a distance. And the Friday after, Professor Elkin Roa from Universidade Industrial de Santander, Colombia, talking about hardware security instance to secure IoT sensors. And I also can advance to you that next month we are going to have also a talk in the series of industry talks that will be with Ensilica, that is a company based in UK. And some of you already know that Ensilica is opening a branch at Porto Alegre. So Porto Alegre is becoming a city with several companies on design and EDA. So there is already here Silvaco, there is already here Real Intent, now also Ensilica. There is also In Place that is being incubated in the our university, and also there is a new company from California that the name will be announced soon. So also, as Thiago Balin wants to put here in the chat, that there is the call for new candidates to apply for the graduate program on microelectronics, and there is scholarships available. So the call, you have to apply between beginning of July till middle of July to start in beginning of August. So thank you again, Yervant, for this very nice talk in a hot topic nowadays.
Thanks a lot. I appreciate it.
And I hope to see you soon in person.
Yes.
Let's see also when other countries will allow Brazilians to travel. As now we have already the 2 shots of the vaccine, but it's not only the only argument to be able to go to some countries now. So thank you very much again, and I hope to see you soon. So after a few weeks, your talk will be again in the YouTube in a recorded version. Thank you. Bye-bye. See you next Wednesday.